Hi everyone. I'm gonna start in about 2 minutes. Unfortunately, y'all are just stuck with me today. Ross is under the weather, so it's gonna be a one-man show. So I'll do my best. It's to kind of get through everyone's questions and all of that. You might have to bear with me because I only have one computer and I will be proctoring my own questions. So I'm happy to answer anything. Just at the end, I might have to do some technology fiddling that didn't expect to do. And you get maybe like 20% less charisma because Ross isn't here. So sorry about that. I think probably take about 30 minutes today to talk. Some of y'all may have heard some of these presentations before. We talk about the Metal X pretty frequently, but I used to like to use this time and space as an opportunity to answer any questions that y'all have about the system or any Markforged systems generally, or that kind of any applications, all that kind of stuff. So feel free to ask anything and I'll try my best to answer it, provided I'm able to. But yeah, so let's launch into it. Might as well get moving. Got 100 people on the line and we'll go from here. So today we're going to be talking about the Metal X, specifically Metal FFF printing, as we now call it. We've previously called it atom or bound powder extrusion, or a lot of different names. Essentially, it's bound powder filament with a coming out of an FFF system. We'll explain in a second. We like to call it the Swiss Army knife of metal manufacturing, and we'll kind of get into why. But the main focus of this is to give you kind of a brief overview of the metal system and how it works, what it's good at and what it's not good at. And then to spend the majority of the time going over about 10 metal printing applications that work really well with this system. And one thing we like to stress with this is that finding perfect applications for the Metal X can be tricky because there are plenty of them out there, but finding them isn't always about figuring out one specific killer app and then just scaling it. So for example, if you think about composite systems, end of arm tooling is a killer application where just about every end of arm tool is going to be better printed with a composite 3D printer than fabricated otherwise. With metal printing, it's not necessarily the case. So these applications end up being a bit more niche or more specific or interesting, but there's uniting factors between them, and there's uniting attitudes that customers that find really great applications tend to take. So that's what we're going to focus on today, and kind of give you a bit more of a stripped back view of why metal printing is interesting and how maybe you can leverage it. So we'll get going. So I'm the only one here today. As I said, Ross is feeling under the weather, but I work in product marketing here for the metal system, among other systems. I've been at Markforged for almost 7 years. I have an engineering background, and I slowly kind of drifted away from it as I've been here. I've kind of seen the Metal X from an idea to what it is today. Ross is the product manager for the system. He and I work together all the time. So he kind of is in charge of making decisions about the future of the system. I'm in charge of bringing customers' perspective. We work as a team and all this stuff. So you'll see us around pretty often. We tend to talk at some conferences and shows, as well as give webinars like this. So that's us. We built this together, so I'll be moonlighting his half. Okay, cool. So first, as I said, we're going to give a quick intro into what Metal FFF printing is, how it works. I'll give you a super basic overview. If you have questions, save them to the end, and I'll try to answer them all then. Strengths and weaknesses. This system is distinctly not perfect. It has things it's good at, and it has things it's really not good at. So one of the key things with being successful with this system is finding parts that it's really good at doing, and then kind of scaling from beyond that. And the last, it says 4, it should say 10. We scaled this presentation out a lot more and recently. So we're talking about killer applications. So first, intro to Metal FFF printing. So essentially, Metal FFF printing starts with FFF printing, but in reality is a 3-step process. So you have your printing, your debinding, and your sintering. So before you kind of get into these specific steps, we need to talk about the filament. So filament for a Metal FFF printer is something that needs to have metal inside of it, but also needs to be at least some component polymer, because FFF printers exist by printing polymers out of a nozzle. So the way that works is we use basically MIM feedstock, if you're familiar with metal injection molding, and that feedstock is metal powder that's encased in a polymer and wax binder. It's kind of a 2-part binder. And so the effect is that this filament is actually kind of waxy and roughly polymer-like, although it's not very similar to any polymer that you conventionally 3D print with. it's printable through an FFF system. So the printer itself is essentially a highly specialized FFF printer that's designed specifically to print this polymer. It turns out that, to make this polymer work, it's not necessarily as taking as well to 3D printing as, say, PLA or nylon or onyx, our filaments. So it's a tricky polymer to print. We print it. It's a highly specialized machine. It has a heated chamber, heated bed, and we print it. And when we print it, we scale it up about 20%. And the reason we do that, I'll get to in a second. So the second step is debind. And so, or debind or wash, they mean the same thing. Essentially what we're doing is we're putting this now part that we call a green part. When you print it, it kind of feels like clay. It's actually magnetic, but it doesn't look or feel like metal at all. We stick it in a solvent bath, and that dissolves kind of the first of the two binders. And that takes a decent amount of time. It basically takes an exponential amount of time based on how thick the part is, how thick the solid geometry is. And essentially the result of that is a part that we call a brown part. It functionally looks the same as a green part, but it has basically micro channels dissolved into it. And then the last step is sintering. So with sintering, it's in a furnace, and kind of within furnace sintering, there's two stages. The first stage is kind of this intermediary stage where we bring it up partway to temperature and we burn out the rest of the binder. And during that process, during that burning out, the part actually shrinks a predictable amount. So that scaling up that we automatically do when we're printing basically shrinks. And so the resulting part out of the sinter is the correct size. And then after we burn out the rest of the binder, we raise it to nearly its melting point. And that's when it kind of turns from a bunch of metal powder pieces next to each other to an actual metal part. So that's the entire process. We provide all the machines. A couple extra notes here. I kind of alluded to it. You can print solid parts on it, but the geometries that work best tend to be thinner. The reason is that if you print solid, the amount of time it takes to dissolve through, the binder it takes to dissolve through kind of goes up exponentially. So that's one caveat. And so to combat that, what we do is we print what we call open cell infill. So just pretty similar to your conventional 3D printed parts. You have walls, floors, and then you have some infill lattice structure. And that enables the debinding fluid to permeate a lot more easily and a lot faster. So we'll kind of get into some kind of print times and time in hand for, print wash sinter for some parts in a bit, but that's kind of an idea of the process. So why does this process exist in the first place? There's metal printing processes that are honestly more precise, that can print larger parts, that can print more intricate parts, all that stuff. What this has over pretty much every other metal process is safety and affordability and accessibility. So what do I mean by that? I mean, firstly, this is one of the very, very few metal printing processes that doesn't use loose powder. So we have powder in this process, but it's bound. So you don't need to deal with any safety equipment, special material handling, all that kind of stuff. It kind of just behaves like a filament while you're doing it. So that's a huge difference. The EHS requirements for something like this are fundamentally less constrictive than those for a powder bed system or a binder jetting system, or even a wire feed DED system, which are maybe the only other systems out there that typically don't use powder by themselves. So that's the first thing. And the second thing is affordable. Metal printing is pretty fundamentally unaffordable as an idea. Most metal printers are going to run you at least $500,000. And then when it comes to building out a special room and hiring someone to use it and doing the installation and maybe doing all that stuff, it's realistically a 7-figure expenditure. So if you're buying metal printing, you either have a really sewn up application for it, or you're someone who just has 7 figures lying around, which there are people that do, but that's not most people. So for this printer, it runs about 200 grand, and that's including everything, install, that stuff. And that's still a pretty hefty expenditure, but that's more along the lines of what a CNC mill costs than what a house-sized manufacturing equipment does. So because of that, not everyone can acquire this. It's still an expensive machine, but it's a machine that a lot more people can competitively think about acquiring. And it means that when you're thinking about a brand new manufacturing method that you're not sure is proven out, that you think you have good applications for, but maybe you need to do some work on, it's a lot more feasible to acquire something like this than something like a powder bed system. And the last thing I'll add is about accessibility. If you're familiar with our composite printers, this printer uses the same software, uses the same slicing. Because it's also an FFF printer, the same basic rules apply. So if you have a good intuition for printing parts on an FFF or FDM printer, you have a decent intuition on how parts for this work out. There are obviously special caveats and things that you need to take into account and learn, but the learning curve is much shallower, and you don't necessarily need a dedicated operator for a machine like this. You can just have it in an engineering facility, and someone can be responsible for running it along with a fleet of other machines that maybe they have their core responsibility for. So those make it a little bit easier of a pill to swallow from an acquisition perspective. We talk about material availability. We'll keep it simple. We do 17.4 pH stainless, A2, D2, and H13 tool steel, Inconel 625, and copper. So we have a pretty wide suite of materials when it comes to functional applications. There's a couple of things that we'll kind of look to add in the future, but from that perspective, we see pretty broad usage. 17.4 is kind of our main material, our flagship material. We see a lot of people use tool steels, and then Inconel and copper have some really interesting and powerful applications on their own. So yeah. So that's kind of the system at a glance. Now I want to talk for a second about kind of what we mean by Swiss Army knife and then strengths and weaknesses. So, there you go. So first, strengths. Oh, I think I skipped a slide. That's what happened. So why do we call it a Swiss Army knife? So there's kind of three reasons that go into this. The first one is that it's really good at solving kind of a wide variety of problems. It can do large blocky parts. It can do relatively intricate parts. It can print with a bunch of different materials. So in terms of the number of problems that a single machine in your shop can solve, this thing is up there. It's really, really, really capable. And also the problems it tends to solve are sticky ones. So like printing copper and Inconel, those are not things that, a CNC mill likes to process. So same with tool steel. So it's capable of doing a lot of really interesting things. And it's fundamentally more accessible. It's, doesn't sit in your pocket like a Swiss Army knife does when we talk about it in comparison to a DMLS machine. It's really accessible. But the big caveat with a Swiss Army knife is you're carrying it around, and like if you look at the scissors on that Swiss Army knife, like if you need to cut something small, those scissors work. If you need to cut like a ream of paper, those are not the right scissors for the job. And so the thing about the Metal X that is challenging for people to understand and for people to adopt and find great applications for is that it is often not the best tool for solving a specific problem. If you are looking for the most highly optimized way to solve a problem, the Metal X often is not it. What it is it's a really good way to solve a bunch of problems, and it can solve problems cheaply and affordably. And so we'll show you some applications later where it is distinctly the best tool. But a lot of these, you could machine this. If you wanted a perfect part, you can machine it, you could broach it, you could cast it, you could do all kinds of stuff. But the reality situation is those fabrication methods might not be realistic for what you can actually accomplish in the context of your application or your business requirement. So, that's the tricky thing for the Metal X, is that people who tend to be successful understand that it's not necessarily that they're doing this because they're trying to create the most highly optimized part. It's that they're trying to create the best part for their business. In terms of more brass tacks, strength and weaknesses, there's three things the Metal X really excels at. The first one is low volume. We do have people using the Metal X for production, but they're mostly using it for a few parts, 1 to 2,000, and 2,000 is really stretching it depending on the size of the part. It's really good at making not that many parts. It's still an FFF printer, and when you think about it, nozzle-based printers are constricted by how fast they can put material out of a nozzle. So that is going to be a forever weakness of a system like this, but a strength from a perspective of if you need to make a few parts, this thing is cheap to do it because it doesn't require tooling or anything special. The second thing is for single parts, it's really fast. It can deliver parts in as fast as a day if you kind of do an accelerated process, but realistically, you can deliver most parts you think about printing on this system in about 3 to 4 days. Like you can think about that as a time frame. What that means is, that might not be fast if you think about slapping something in a mill, but the reality of your business situation is probably that your CNC facility has a queue, or you're sending it out to a third party, or maybe you need to make tooling for a complex part. And so, while technically on machine time, it might be slower, the reality of getting a part in hand is often faster. The second one, which kind of alluded to in the first bit, is complex and high mix. So customizability is a real big thing here. We'll talk about prototyping and how you can kind of parallelize design progress with a system like this. But the big thing is no tooling, and complexity inherently, if it's printable, is free. Adding a feature is not something where you have to think about what machining time, how much does that increase my machining time, labor, difficulty, all that kind of stuff. Last one we already talked about a bunch of times. It's accessible, no dedicated operator. It manufactures overnight on weekends, doesn't need supervision when it's kind of in process. And it's simply piece of software. So that's the starting point of why it's good. Why is it bad? So kind of the opposite of what we just talked about. Like high volume and low mix is just fundamentally not for this. We have our new kind of binary genetic system from Digital Metal, the PX100, which I'm sure you'll hear much more about in the future. That's much better for high volume, low mix. You know, if you're thinking the thousands, that's something where you're within scope. But if you need to make thousands of parts a year, like this machine is just fundamentally not fast enough. And if you can parallelize these machines and build a big print farm, but at that point, you know, you're kind of stretching the limits of the technology. Once again, we talk about mix, like high mix versus low mix, we mean part variability. So if you're making 5,000 of the same part, that's low mix. If you're making 500 SKUs and you're making 10 of each of them, that's high mix. So low mix is not great. High mix is really good for this printer. Precision tolerances are a key. So we talked about shrinkage. This machine can hit some tolerances depending on the geometries, and you can easily post machine parts or post grind parts or post process them in any way to hit tight tolerances. So if you have something with a couple tight tolerances and more like near net shape, that's fine. But what you can expect is that the off machine tolerance of this is going to be anywhere near what you're going to expect from a CNC mill. And what I will say is that some people tend to print very complex geometries or thin features, and those are tons of things that are kind of furthest from the least accurate that this thing can print, and then they expect tight accuracies, and that's tough. It's just with this process not realistic to expect, and you know that's okay. It's kind of a process constraint to make something accessible and relatively easy to use and safe. Sometimes you trade some things off, and accuracy, if like tight accuracy is one of those things. The way you get around is post machining. You can do it. It's totally feasible. It machines just like any other material. You can also heat treat parts just fine. So if you need to machine and then heat treat to harden something up, you can do that. And the last thing is really big and really small parts. So I like using this analogy. It's like thumb size to fist size is kind of the wheelhouse of this. And the reason is that with that shrinkage, the way I used to think about it is like the idea you don't see any T-Rex sized birds. The reason is because if a bird gets, 4 times bigger in every direction, it's actually 64 times heavier. So it's the rule of cubes. So the same thing happens with shrinkage and volume. So, you know, just when something's shrinking 20%, it's actually losing 40% of its volume. So the larger it is, the more shrinkage happens, and the less likely it is to kind of stay stable. So you can go larger depending on the part, but generally that's kind of the size, the top end of the size constraint. And then the bottom end of the size constraint is basically due to the nozzle. So when you're printing with the nozzle, your feature size is constrained by the diameter of your nozzle, versus 400 micron. So printing features larger than 400 micron minus 20%, the shrinkage factor is really difficult. So those are the type of things where we kind of see the edges of the system. And at the end of the day, like there are a wide variety of parts between that size, but a lot of people have parts that need to be larger or smaller. And those are parts that are just not optimized for the system. So this is a bit of a summation of what I just talked about. If you want to screenshot a slide, this is probably the most useful slide to screenshot, just as kind of a guide to what works and what doesn't. What we mean by ideal and limit is kind of what I just described. So ideal is like what we think the wheelhouse of the machine is. Limit is generally what it's capable of. So you'll see parts that are much smaller than thumb size that work great. And you'll see parts that are larger than fist size that work great. But they're not kind of necessarily in the wheelhouse. And then we talk about tolerances. You know, we're near net shape, but in some areas, the tolerances can be a lot better than that. Yeah, so I'll go on that. If you kind of want to look at this, I would just recommend screenshotting and looking at it later, because I don't want to go through the big table. I have more fun things to talk about than that. One of those is what I call the X factor. So we kind of talked a little bit about speeds and feeds in terms of what this is good and bad at. And if you've seen me present before, you maybe have seen this slide, but I kind of harp on it over and over again because I think it's really important. This is one company's example, but you know, we've seen this with just about every company we've talked to, where one of the biggest things about bringing something like a metal 3D printer in-house does is it actually empowers your employees. So what we talk about is that empowering employees is not just, you know, your shop employees or your CEOs, it's top to bottom. So if you look at kind of these quotes from top to bottom, the CEO talks about how it's removing bureaucracy and adding autonomy, which is good for him. Director of engineering talks about how his engineers are more invested in the tasks they can do because they are able to see the results and able to kind of have more granular control over what actually they're designing and how it's being made. And then the model maker, the people in the shop who are previously nervous about kind of this taking their jobs, are suddenly become one of the biggest advocates for this because it ends up making their job easier. I think we're kind of well into this kind of back inshoring of parts and processes. And one thing you see is that there's more work than jobs to be done, and so there's more work than people to do it. So what that means is if you can have something that helps you be more efficient, it ends up being better for you in the long run. So yeah, so that's enough about strengths and weaknesses. Let's talk about some killer applications now. So first, before we talk about applications, I want to kind of touch briefly on this kind of as like a heuristic for how we think about this. So first, what is a killer application? You'll hear every salesperson and just anyone who's talking about 3D printing talk about this all the time. As it's defined, it's really just an application that is fundamentally indispensable. It becomes something that's so effective that there's no reason not to do it, and it's so vastly superior that it's a slam dunk. We think about categories for applications here. We think about rapid prototyping. We think about building durable tooling. That durable is really important. We talk about one-off spare parts or kind of MRO replacement parts, and we talk about end-use parts. So those are kind of the kind of four classes. And then we think about requirements. So one thing to think about is that one of the biggest reasons to not buy a metal printer is because a composite printer can do the job that you need to do. And what we mean by that is that composite printers are great for a lot of the things we just listed in that left side, which is they're great for rapid prototyping. They're great for making some tooling, MRO, and end use. But there's a set of requirements that composite parts or plastic parts just fundamentally can't match because they're still plastic. It doesn't matter how much carbon fiber you put in a nylon part, it's still based in nylon. So we talk about really, truly high strength parts or parts that have a lot of wear resistance and heat resistance and corrosion resistance, or parts that are conductive. Those things are just factors that composite printing does not accomplish. And so those are places where if you have those requirements for your part and they're a hard requirement, you need to go to metal. That's the only way to do it to accomplish your goal with 3D printing. So yeah, so with that, let's talk about 10 cool applications, and happy to answer any questions about these. I know them pretty well. A couple of them Ross knows better than I do, so I'll do my best, but I will go from there. So the first one, so this is a company called Caldwell Manufacturing. The company actually that we talked about is kind of the X factor. And this is one of their many applications, but it's my personal favorite. So often 3D printing is cast as a kind of a prototyping tool, and people who make 3D printers who want to kind of go beyond that and become production don't love hearing that. The reality of the situation is that 3D printing is a great prototyping tool that's also great for a lot of other things. But when we think about prototyping, one thing in kind of the modern era is beyond just being able to produce a part that looks right. What does being great at prototyping actually mean? And Caldwell has kind of taken this idea and supercharged what they can do with prototyping. So if you look at the top image, what you see is those parts look functionally the same. They're all a little bit different though. And if you look at the bottom part, you can see there's tons of different little pieces of hardware that they're printed out of both metal and composite parts. And so what they realized pretty quickly is that what they can do is they can totally reinvent their prototyping cycle. So for them, they have something like 100,000 SKUs in their operation. They make windows and doors. There's tons of tiny parts and a lot of customizability. And so they need to kind of get from idea to part signed off as soon as possible. And what they were seeing before is that they would have to basically send parts out to their machinists, bring them back, send them out, bring them back. And that iteration would take weeks and weeks and weeks and stretch into maybe even a quarter for them to actually get something right, and thousands of dollars. What they realized with 3D printing is these parts are materially wise dirt cheap, and they don't take that much time to print. So what they can do is they can print 20 different design iterations at one time. And what that means is that instead of finding out one thing from one iteration, they can find out 20 things from 20 iterations. So like 20 parallel iterations. And that means that they can settle on a final design so much faster. They can say, oh, well, this feature of this part ended up working out really well, and this feature of this part worked out really well. Now we can kind of see that this is the direction we need to go. And if they can do that, and if companies can do that, it basically totally changes how iteration works, because all of a sudden you can take this typically low customizability fabrication stack that you're working with and make it super high customizability. So that's a really cool application. They've been using it to great effect, and they kind of print tons of parts at once and figure out what's right and then go from there. So moving from prototyping to tooling, a lot of prototyping stories kind of sound the same, so we won't belabor that too much. So this is a classic example of one where a part where like a high power composites user kind of finds what the logical end to using composites is, and then figures out that metal is the right way to go. So These robotic grippers are gripping the inside of threads, which are fundamentally abrasive, especially on cast parts. And the result of that is that even though they're reinforced with, I believe, fiberglass or carbon fiber, it doesn't really matter which, they wear down. And so, like, we're not talking on the order of like 20 cycles, we're talking on the order of 10,000 cycles. And so after 10,000 cycles, these grippers are rendered non-functional because they just don't have much to grip anymore. They're totally worn down to the studs. And so that's fine. 10,000 is good, but if you're making several thousand parts a day, that's only a few days. So what that means is that despite composite being a great solution for some tooling, for other bits, it just doesn't solve the problem. So what if we print something out of tool steel instead? So it takes longer, costs more money to print this out of tool steel, but instead of 10,000 cycles, you're talking 1 million plus. You're talking about this is functionally a tool that will last as long as you need it to. And suddenly then you have, instead of a consumable SKU for your tooling, you have a tool that lasts, beyond what you need to think about replacing it for. So that's a huge change. And it's a big way to kind of reduce the number of parts you have to keep in inventory of terms of spare parts. Looks like there's some questions, so I'll jump in for a sec. Okay. Some of these are just, I'll get to these at the end. They're just printing details, which I can get to. Okay, cool. So going from tooling to kind of replacement parts. So it's a great example of kind of like your perfect MRO story. So when you think about MRO or like a one-off replacement part, the classic example is something that was made a long time ago that's no longer made. This is exactly that. So this is a carburetor for like a vintage car. And they had two on the car, and one of them was like cracked in half, and it didn't work. And they functionally, for the project they were trying to do, this was basically a service bureau printing for this job shop. There was no way for them to make that part or machine it that was cost competitive, that was worth it for them to actually go through with it. So essentially they were kind of stuck. They had no way to replace this part. They could have maybe jury rigged something, but probably wouldn't have worked. In comes 3D printing. So the interesting thing here is that what they did is first they scanned the part, they scanned the one functional part. They then printed it out of onyx or plastic to see if it would work. And what that meant is that they could actually bolt the part on as like a looks like or kind of stand-in prototype just to make sure their measurements were right. They bolted the plastic part on, it worked great. And so they progressed to printing with metal. And so they experimented with a few different orientations on how to print this part because it's pretty challenging. It's got a bunch of holes in a bunch of directions. The bottom is a cavity. It's got to be sealed. All this has a lot of requirements. They found one that worked. They printed it. They knocked all the supports off. They tapped the holes and they put it on and it just worked. And the result was that this part would have taken months and months and months for them to make properly, thousands of dollars. They wouldn't have made it, frankly. And they were able to make something for a few $100 that was functional. And this is my favorite bit, the next picture. So if you look at the left carburetor here, that's the printed one, and the right one is the cast one. And they both work, and this car runs still. So it's a great story of how you can kind of take something that you never could have imagined fabricating or it just didn't make sense to make anymore and make it. Okay. So this is an example from something hyper bespoke to something basically something you could buy off the shelf. So this tool bushing here is a D2 tool steel bushing for a drill jig. And frankly, this is something you could probably buy from a supplier that's relatively standard. You might need to machine a groove in it, or you might need to drill it out custom sized, but it's something you can maybe buy. But the reality is that if you buy something, that takes time, and lead time is time that you can't be doing something else. So for a part like this part, imagine a scenario where this tool is the thing holding up production on an aircraft or a helicopter. And you need that one bushing to work. And you could either wait 2 days for it or 3 days for it or a week for it to kind of get it right and get it machined, or you can print it and it'll be there tomorrow and it'll be $20 and relatively functional. So it's an example of sometimes your tooling can't wait. And the cost of you not being able to do an operation because of tooling is much greater than the cost of anything else. So the priority is time over everything. And we see is that the metal printer tends to work really well in scenarios like this, because especially for these small parts, it can kind of deliver them no questions asked in a day or two. And the reality of the situation is that there are very few parts that are non-perfectly standard that you can get in a day or two. And that is a huge difference maker when it comes to keeping your lineup, keeping things running, keeping high value manufacturing operations going. All right. And then from something very standard to something that is super non-standard. So, I talked at the beginning of this presentation about how most parts were not kind of the most optimized solution. What we're working with here is parts that are, this is the best way to make it, but it's maybe not the best possible version of this part. This is not one of those. So this is an example of where 3D printing, especially metal FFF printing, really shines. So this part is copper and it's a tool cooler. So essentially this is a high volume milling operation. And the way they lock their tools in is they lock them in thermally instead of kind of with a standard chuck. So they heat the tool up, the tool expands into the chuck. It then holds it in. To get the tool out, they need to cool it down. So the amount of time it takes to cool the tool is the critical kind of element of the changeover time between tools. So if you have multiple operations, you need to do this with multiple tools. So this part is called a tool cooler. There's fluids that kind of percolate through it constantly, and it's heavily vented, and it's copper in this case because it needs to, kind of absorb as much heat as possible. And previously they made these out of aluminum because machining copper is basically impossible. And aluminum is just less good at kind of taking heat off of stuff. It can carry less heat, and also machining kind of limits the number of geometries you can work with. It limits the amount of surface area you can have on a part. It limits the internal channels greatly. So you really can only do so much with an aluminum part. With a copper part, you can print something like this with tons of internal channels, greatly expanding the surface area so it's able to radiate heat outward. And the result is that this design that they came up with is ultra high performance. So what we mean by that is that the tool cooler was able to basically cool the tools 40 seconds faster per change. And what that meant for the kind of operators was 111 hours a year of saved time on this machine due to decreased changeover time, which is thousands and thousands and thousands of dollars just by implementing a single tool. So there are cases in 3D printing where if you're looking for hyper optimized to kind of get to that ideal performance state, 3D printing is the way. All right, on to the next. Oh, my computer is struggling. All right, perfect. So another kind of hyper optimized, low volume, specialized end use part. So we work with a company called Goering. They have one of our printers, and Goering makes cutting tools. You've probably heard of them. They have thousands and thousands of cutting tools. Some are ultra high volume, some are ultra low volume. For a lot of their kind of closer partners, it ends up being that the partner is asking them to make a few very specialized tools for a highly optimized operation. And at the end of the day, what that means is that the customer has to find the money to help Goering develop the tool, to make the tooling to make this cutting tool and all that kind of stuff. And for Goering, a lot of these are just they can't offer a competitive cost for this. And so a lot of these projects end up going towards more standardized tools, or they only choose to do stuff like this if the piece of tooling itself is so high value for the customer, they can pay top dollar for it. 3D printing really changed that for Goering. They had an idea. They were like, what if we can print these tools? We can post machine them. It takes a little bit of time. We'll braze carbide tips onto them. But if we can make these tool bodies and we can put kind of specialized cooling channels and all this stuff in them, and they work, that can be a huge new business stream for us. What they've seen is, they tried one and it just worked. And so what they do now is they work with some of their kind of highest priority customers to develop super specialized tools that they print, and then they send to the customer as the end article. And that means that the customer gets a more highly optimized tool for a competitive price. And it means Goering can open up new business streams based on hyper specialized end use parts. So again, we kind of go back to low mix, high mix. This is the ultimate kind of high mix end use production example. They have parts where they only need every production part might need to be a little bit different. And they're able to kind of accomplish that really only with metal 3D printing from an economics perspective. So that's a super specialized tool that functions as a use part. This is like basically a very simple tool that ends up being most optimized to 3D print with both composites and metals. So earlier when we talked about the end of arm tool, we mentioned that we were talking about replacing composites with metals. In this case, what we're doing is we're combining them to make something that's more optimized than either tool itself could be. So this is an example, a representation of a tool that one of our automotive customers used to basically transport huge cast bodies from one location to another. It's just a single machine basically pulls the tool along. And this part's really heavy. The tool needs to be heavy duty. It's obviously a metal casting, which means that it's going to wear out a plastic tool. Previously, they were machining these whole big bodies out of tool steel, and one kind of extenuating circumstance that caused them a significant failure was that the machine failed. It kind of went past its boundaries, and it crashed the tool into kind of the end of the machine. And because the tool is tool steel, it basically broke the entire machine. Imagine it's like, running an end mill into the stage so hard that you break a spindle like that. Like that's basically what happened with this tool. And so they were searching for two things. One, they realized that composite tools by themselves were not going to be good enough to not going to be durable enough to kind of do this operation many, many times. But they also realized that if they would prefer is the tool to be the failure point, not the machine itself. So they designed something like this, where you have a multi-part, composite appendage that is strong, but will still break before the machine itself. And then you have super high weight, super resistant H13 tool steel inserts that you can, bolt and unbolt if you need to pretty easily. So that means you kind of have this combined tool where previously you have this, 10-pound, 5-kilogram tool that costs you $2, $3, $4 grand to make. And now you have a tool that costs way less, that is still functionally as good, if not better, for the lifetime of your machine, that costs you $100 or $150. So huge difference there. And we see hybrid tools for people that work with both composites and metals as big difference makers when it comes to combining the capabilities of metal with the capabilities of composites. Only a couple more here, and then we'll jump to some questions. So this is another tooling example. Tooling is kind of the talk of 3D printing, especially in metal 3D printing. This is a consumable tool. So this is a copper weld shank that's used for robotic welding in kind of the automobile industry. And fundamentally, this is a consumable tool. After about 500,000 welds, a tool like this is no longer viable. And that sounds like a lot, but that number that doesn't take that long for a robotic welding machine to accomplish 500,000 spot welds. And so the thing that the automotive customer that we're dealing with here ran into over and over again is they had to keep a huge number of these parts in stock because they were concerned about them. And to make a part like this highly specialized copper machine part, they had to kind of order them in large quantities, and they would take, weeks, if not months of lead time. And essentially, because of the constraints around fabricating this part, they had to jump through a bunch of hoops to keep it in stock and to make sure that their line wasn't down, because that was their number one priority. What they see with 3D printing now is that they can print these parts in 3 to 5 days. And so that by itself is not a huge difference maker. But when you compare it to the traditional method, what it means for them is that they don't need to, think 2 months ahead when they're trying to replace these parts, and they don't need to keep a ton of these in inventory. If they see a part that's at 350,000 cycles, they can just print a new one, and by the time that thing is done, they'll have that one part needed to replace them. So for a large company that is keeping thousands and thousands and thousands of tools in inventory at one time, reducing inventory even by a single part is a huge difference maker for them and saves them thousands and thousands of dollars a year. And you can imagine that with the way this works, if you see other consumable tools, this ends up being a way for you to reduce your tooling spend across the board. It's a really easy thing to scale in the context of that. All right, 2 more. So this is a production part we've kind of talked about before, if you've maybe seen it. This is an Inconel part, and the interesting thing about this part is it's a low volume production part. Not too many of these are made a year. It's made on this it's made for this super precise like low volume machine that is basically made to produce metal samples at ultra high temperatures. So this needs to be Inconel because it's subjected to super high temperatures. They call it a crucible clip. That thing that sits inside of it, it's on fire, is a crucible. So the person the company who makes this, called Nika, they previously got these machined out of house because they didn't have Inconel machining capabilities in house, and that was very expensive, and they were kind of at the whim of the supplier. So they actually went to powder bed printing, but they went to powder bed printing via service bureau. And so they basically reasoned that if machining was a pain, maybe powder bed printing wouldn't be. And they found it was less of a pain. It costs a little bit less, but it still took 4 weeks of lead time for one of these parts to be finished, and $400 a part. And to Louis, the guy from Nika, that didn't feel right. And so he went and thought about buying a system, and kind of looked at Markforged and asked himself, would this actually accomplish the job? got some test parts, put them on his machines. They worked great. And he reduced, a 4-week lead time and $400 to a day and a half and $50. And that means that for each of these machines, which has 4 of them, he's saving about, more than $1,000 in COGS, cost of goods sold, per machine. That's a huge way. That's a great cost cutting measure you could take with a single move. He's expanded to make other parts within this machine as well. And so, but this single production part ends up being a huge difference maker. Okay, hopefully it doesn't double. All right, so then this is the last one. This one's my personal favorite because it's just the strangest, but one of the most interesting applications that turns out to be just a total slam dunk. So this rather spiky looking part is what's called a fish descaler. So in a fish processing plant, they need to get the scales off the fish. There's a bunch of processes. There are a bunch of processes that go into this. I'm frankly not an expert on this. One of the parts is this thing that actually takes the scales off. And if you look at this part is, like, by conventional metrics, almost impossible to make. Like, there's just not a lot of good ways to make a part that's shaped like this. And in fact, before they found 3D printing, the way they were making these was kind of creating like a Franken part out of a bunch of welded sheet metal pieces. And it sort of worked. It sort of didn't work. It broke a lot, all that kind of stuff. So it was very not optimized, but it was the only way to kind of get a part with this geometry. As it turns out, there's some parts in the world where 3D printing is just so much better suited to making a part that it's just an obvious win no matter what. And if you look at this part's pretty easily printable. There's no geometries that are too thin. There's no overhangs that are crazy. It's a pretty simple part to print in the end of the day. And so what he did is he ended up reducing his part count a massive amount. He eliminated this welding procedure that kind of created a Franken part and really optimized his tool. And so it's a crazy part. I have a video or a GIF on the next page to kind of show what this thing does in operation. But essentially, this is a totally weird thing that, I had never heard of a fish descaler before this. This is not an application where I could go and, look it up and be like, oh, I'm an expert on fish descaling. What's the right way to make this part? But this person who was an expert on fish descaling, who made these machines, realized that this capability that he had really matched well with what he needed to do. And that's a great way that a lot of our most successful customers find their way into applications. So yeah, so this is the actual machine. You can kind of see the spinny bits. These things are spinning at ultra high speed, and that's actually the part itself. It's faster, it's cheaper, and you can make more of them more easily. Before I answer some questions, I want to kind of pose this as kind of the last challenge or so to kind of ignite questions and ignite thought. So what makes a successful manufacturing company? There's myriad things. It's not like there's a single thing, but one thing that Ross and I really agree on is that there's two kind of tenets that we see that kind of unite the most successful manufacturing companies that we work with. The first is that companies that make products with the best user experiences. And so when you make the product with the best user experience, there's no way to kind of like luck your way into user experience. It takes creative designs. It takes iterating over and over again to make sure something really works. And it takes de-risking to find your failure modes and take them out. The nice thing with user experience is that it's not really only a savant user designer designing something perfect. It's a lot of hard work and iteration to make something that really works over a long period of time. And the other side of it, the kind of much more operational side, is companies that make products with the highest cost efficiency. So who is the best at making a good product cheaply for them? And if you make it for higher cost efficiency, you can charge less for it. You can make more money. Your margins can be higher. There's tons of ways that this helps your business. And we see here is that these people need to kind of like custom tools or kind of novel ways to make parts. They automate processes where they can, but they make sure the automation they're working on is robust. It's not kind of flimsy and only optimized for like the edge case of when it's going to work. And they're obsessed with continuous improvement. They're always finding ways to make something a little bit better on their line. It's never a finished article. We see, between these two things is that 3D printing is an enabler. It's not the thing that will make you do these things, but it's an enabler to help companies deliver on these great customer experiences at like the lowest possible manufacturing cost. So if you look at these applications and what unites them, you'll really see that most of them fall into kind of one of these two camps. Yeah. So that's the challenge is how are you kind of bringing yourself into one of these two camps, and how can you make 3D printing something that works for you? And with that, I believe it's time for questions. If my thing agrees. Oh my gosh, it's clicking weirdly. All right. Let's see if Zoom will handle this for me. Oh man, what is happening? Okay, perfect. All right, so questions. All right, so I'll open the question pane and just see if I can get through these as quick as possible. Feel free, again, shoot anything. I'm happy to go till the top of the hour. Obviously you've been here for a while, so no need for you to stay if you don't have any good questions, but I'll try my best. Okay. Is there a market in South Africa for which you're aware? I believe we do have printers in South Africa. We definitely have composite printers. I'm not sure if we have a metal one. I think we have like a reseller or a partner down there, but I'm not sure. Someone asked what the minimum thickness for copper is. So right now, the minimum thickness is like roughly 0.8 millimeters is kind of what I would say is the right one. But I would say that we're actually about to release something that it's going to kind of really improve fine features for first copper, but in other materials, that we've kind of been doing some algorithm magic to kind of go beyond what our previous capabilities were. So stay tuned there. I think we're probably going to announce something in the next couple of weeks about that. So just that's a cool kind of step forward that you'll see as well. Do I think SLS will be as accessible as a Swiss Army knife? Maybe. Like, there's the problem with SLS is that, like, the problem with all these processes fundamentally is that metal printing requires two things that are tough. One is like I would call like voxelized metal, so like metal in a form that's small enough that you can form it, because metal bonded together you fundamentally can't like reform. So powder is the most obvious way. And the second is like a very high energy process. And so for our process, the high energy process is in our sintering furnace, which is nice because it's consolidated, but it also means we have a very, intricate sintering furnace. SLS, the high energy process, is the laser that puts it, that kind of melts it together. And so because SLS by nature has a laser and powder, it's always going to be tough for it to be accessible. There are some SLS or SLM, which is kind of the metal version of SLS, or DMLS, whatever you want to call it. There's some machines out there that are cheaper, that are kind of in the same range, but their build envelope is like really small, and that their maybe reliability is a bit lower. So it's possible, but it's always going to be a tough technology to be super accessible. Someone asked, what's the service roughness? Would they require tooling to reduce roughness? Off the top of my head, I don't know what the roughness specs are. It depends on the print mode, and it also depends on what face. So obviously the side has layer lines and the top is kind of printed like with a roof and a floor, and those offer different roughness values. In terms of the other side of the question, reducing roughness is actually really easy. You can post machine it, you can polish it. You can, like, one thing you can do that's a little bit less accuracy related and more cosmetic related is you can actually like wet sand the part after printing, but before sintering. So there's a bunch of ways you can make a part. You can make a part smoother. The most reputable is far and away like machining or polishing, and those things work, or grinding, whatever you want to do. Those work fine on a part like this. Okay, someone said the maintenance and what's required. The maintenance by myself, or is required specialized knowledge? It depends on what maintenance you're doing. If a machine breaks down, might need like one of our resellers to come on and fix it. It doesn't happen very often. In terms of like regular maintenance, yeah, you can almost certainly do it yourself. When we install a machine, we train people how to use it. The printer itself is extremely easy to use. The wash is essentially a large cabinet with solvent in it. The sinter requires a bit more kind of understanding and skill to operate. You need to bring gas into your facility. You need to hang a gas panel on your wall. You don't necessarily need to punch holes in your wall, but it does take a bit more kind of expertise to operate. So, but we do offer training on it, and we never sell a system to anyone who we don't feel is confident that they would kind of be successful with it. So I'm sure you kind of get over the hump with that. Which direction, maximum shrinkage, final part? Okay, so shrinkage is an interesting one. So what I think about it is this: if you were sintering in is like a zero gravity environment, the shrinkage would be as close to perfect as your distribution of powder in the part, which is pretty consistent. So what makes shrinkage imperfect is two things. One is gravity, and two is the friction that gravity causes between your part and the stage. So with gravity, like the way you get around that is essentially you can either like design for parts to shrink a certain way, which is which is kind of very tricky and something that we're working on, but we don't have perfectly. Or you can just kind of adhere to some basic guidelines to don't make any towers that are too tall, don't make things that are cantilevered out, and your shrinkage will generally work. We also have supports that handle most of that stuff in the first place, that kind of handle most of the shrinkage and make it normal in the first place. With the friction, what we do is we basically print a raft on all our parts, and that raft ensures that the kind of the center of mass of the part is on under the raft. And so we mitigate the effects of kind of friction. If you imagine a part that's shaped like this and it shrinks, it might do something like this based on friction by having a raft under the part. Is the shear strength of a metal part dependent on print orientation, or are the parts equally structurally sound in all directions? And then there's another one that right below that asked, what is the density of the final part? So these actually have both kind of a relatively similar answer. So when we talk about shear strength or density or any of these things, it kind of depends on how you slice the part. So I mentioned a lot earlier in the presentation that you can print parts that are solid, but it's not necessarily recommended above a certain part thickness. If you print a solid part, we have density specs on all our data sheets. It varies a little bit from material to material, but it's in the range of 95 plus, 95, 97, I think, for most materials. You can check the data sheets, they're readily available for that, but that's the kind of rough spec. And likewise, if you have a part that's printed in and printed and sintered in that direction, it's not exactly the same Z strength, but it's pretty close for the same Z strength that it is for X and Y. Because it's the sintering process altogether. What causes Z strength issues on a plastic part is that the part is cooling, and then you print another layer on a cooling layer, and you kind of do that over and over again. That becomes thermally a weak point. And so that doesn't exist for metal printing because you're sintering it all at once. That being said, to both of these, our typical parts have, basically they have voids in the inside of them. We print with open cell infill. And so the result of that is that shear strength is fundamentally weaker than pull strength, because there's less surface area between the parts because you're printing with that infill. And likewise, density of final parts is not at anywhere close to 95%, but I call it design porosity. You have a porosity in the center of the part. So depending on your part size, you can absolutely print solid, and it kind of solves the two problems and gets you much closer to kind of your base spec. But most parts we print don't kind of adhere to that. What's the exact percentage of the filament metal binder? I don't know the exact percent. We definitely don't publish it. I mean, it's, we shrinks 20%, so it's in that 40% binder range. I'm not exactly sure, but it doesn't really matter functionally for customers. Someone asked same question about fine feature size. 100 micron features. 100 micron features would be a stretch, I think. Even with our new kind of our updated finer feature stuff that we're working on. Titanium filament, we don't have titanium right now. It's technically possible, but it's not something that we're kind of working on at the moment. Someone said, I said the green part is slightly magnetic. Can I elaborate on that? Sure. So a green part has, by volume, more than half metal. It's a lot of metal bound together with plastic, and that metal, especially if it's in this case I was talking about as a steel part, steel is magnetic. So the part itself actually is magnetic. The powder in the part is magnetic, but it's not. Because it's by volume or by mass, a lot of metal in there, but it's not actually a metal part in any kind of conventional way. Cost per kilo of material. It depends on the material. I could get you the exact numbers. I don't want to be, it's like less than 100, but I'm not sure exactly what it is. It depends on the material. So we can get you that detail if you want. Someone said the South African partner, will metal 3D printing be accessible, affordable for hobbyists at home in the near future? There are some technologies out there today that are basically enabling you to retrofit an FDM printer, an FFF printer, to print with roughly similar filament. BASF is kind of the company that does that. And I know that some hobbyist printing people like Ultimaker have, built some stuff that enables you to print that. The issue then still becomes sintering. So you're going to have to send a part out to debind and sinter it. So it depends what your definition of affordable is and like what your standard for part quality is. Like, I think the part quality there is still pretty low because you can't control every aspect of the process. You still have to send a part out, which takes time. And I think the sintering still is relatively expensive. So I don't know if it's it's on a path to being ready for hobbyists per se, but it might get more affordable if you're kind of willing to dip your quality standards. Is the extruder nozzle exchangeable? Yeah, our nozzles are wear components. So they're pretty easily swappable in the event that jams happen. Can you bend, crimp, and form copper after printing? Yes, to a degree. One thing I'll note is that MIM-based filaments result in, like any MIM, this is like not just Markforged, results in parts that tend to be a bit more brittle than like a standard wrought part. So if you look at like our elongation at break is a great example of how brittle a part is. Typically our elongation at break for our like post-sintered parts is slower than you would expect for a wrought part. So I would be a little bit worried about crimping, maybe bending, forming, that kind of stuff. You could probably do it, although you definitely want to test it out first. How do you scan parts to print? You get a scanner. Like we don't sell scanners, but there are scanners out there. 3Dents has some. We did a webinar with them, I think, pretty recently. There's a bunch of scanners out there. If you look it up, there a lot of companies make really good products there. Does printers do internal holes and voids? Yes. So one detail about the printer, it can print about 45 degrees from vertical or from horizontal, unsupported. So if you want to do a hole or a void where you can't access the supports, that's kind of your limit. But generally it's not too hard to actually design parts like that. You know, you can design parts with kind of a structure like this on the roofs and it'll print them just fine with no supports. What are the largest dimensions we can provide? So if you have like a long skinny part, you can probably print it up to like 250 millimeters. In that range. The maximum, like our build size is about 300 wide and it shrinks about 20%. So 250 is about kind of the rough number there. But it depends. You know, you wouldn't want to print a full build size thing that's 250 microns long. But if you have like kind of a longer, skinnier part, it's certainly feasible. Does the FFF printer also print composites? We have composite printers. This one does not. It's just a metal printer. So someone asked about the tool cooler, and said it was the complex geometry support structure could be a problem. So that part, if you actually go back, I'll see if I can get back to it without my computer dying. So if you look at this, all these are designed as triangles, and that kind of gives you and these kind of have these 45-degree angles here. If that gives you a hint, essentially what is happening there is all these things have that 45-degree angle I just talked about. So there's actually very few, if any, supports in this part. So the way to think about it is that if you want to succeed with the kind of complex parts, the way to try to do it is design around without supports. Durability of the components we print, our stuff's on our data sheets. And then holding pressures and leak stuff is really tricky with this type of process because you're laying stuff down with a nozzle. So it ends up being like you end up having natural voids. We do have we've been working on like leak resistant stuff. And it is moderately pressure resistant, but it's not something you're going to make like a conventional pressure vessel out of. How often is the wash fluid changed? We have guides for that. It really depends on how often you use it and how much material you're processing once, but it's not super difficult to change, maybe on the order of like once a month or once every couple months is typical. If you have online training for the sintering system, no, it's usually on site because you're doing it when you're installing a machine. Talked about density, lead times. Okay. We're not printing in aluminum. Right now our stuff is not FDA certified. Are there any installations in yachts? I don't know if in yachts there are any installations, but we have printed parts for boats of many types. And then someone asked about sintering time, and I'll take that as the last question because we're at an hour. So for sintering time, it's actually set. So sintering time for our system is not dependent on the size or the amount of parts you're sintering, unlike some other people who do similar processes. And the reason for that is that we're circulating gas to the system, and we're basically doing the debinding, one of the debinding steps before. So that's a big help for us. In terms of sintering time, depends. So we have typically, I would say about a day or like a day and a few hours. So 25 to 30 hours is kind of a typical sintering cycle. It varies by material. We have an express mode for 17.4 that's 17 hours, and that's for if you need like a single part. It's like up to 250 milligrams mass for a part. You can sinter in 17 hours all at once. It uses way less gas, it recirculates, and kind of is slightly faster and a lot cheaper for that cycle. So that's one way to get around it, but generally about a day is kind of the rough, kind of my rough like metric for how long it takes. All right, well, that was amazing. There's been 40 questions. I think I hopefully got to as many as possible. I'm sorry if I sped up at the end. There were too many for time. I really appreciate you guys taking time with me today. Yeah, it's been great. And yeah, if you have any other questions, feel free to shoot us an email or reach out and, through our contact us forms or any other way. Our sales folks are always available as well, and they're happy to answer questions. But yeah, so thanks all. Have a great rest of your day.